do? Hi guys. Right guys, let's just do our tendons first. It's sunny, yeah? Yes. Let's just wait for Lydia. Okay guys, we finally have summer, right? Everybody's dressed in summer clothing. Right. Good afternoon, welcome back. So, we've been speaking in the revision class, Kitty. We've been speaking about magnetism and forces, specifically forces on a wire in a magnetic field, if there is a current. Nuclear and good Raymond. And so we want to extend those ideas today. So this is still revision. And we're just going to run through a few concepts that we've been talking about and try and get from magnetism and magnetic forces to electromagnetic induction. Okay, so where do we start? I mean, we start with something simple like a magnet, right? And you can see we've got a few magnets here in front. I'm going to hand these out to you guys at this stage so you can have a magnet. And I want you, not everybody, but you can see one side is red and one side is blue, and the red represents your north. I'm going to hand you, please don't hurt yourself. Okay, I want you to see that this wire that I give you now, this piece of wire, is made of mostly nichrome, which is, you can test it on the magnet. Test it on the magnet. Does it pick up the nichrome wire? Does your magnet pick up the wire? Yes or no? No. No. You can try, but nothing will happen. Nothing will happen, right? It's not magnetic. Okay? The most magnetic material is, Stephen, what is the most magnetic material that you have? Iron is right. Not this, right? This is nichrome. Nichrome, yeah, it's not magnetic. Nichrome, I'll write it down. You have a nichrome wire. Okay, to your magnetic, you actually have four materials that are very magnetic. Iron is one of them, nickel is one, cobalt, and then one tantalonium, I think, but I can't remember the slide exactly. It's one of those ones at the bottom of the periodic table. So it's not one that you will work with very often. Okay, so we've been speaking. Thank you, Lydia. Guys, you can put your magnet down now. We'll get back to your magnet and your wire in a bit. Okay? We're going to get back to this in a while. There's a reason I gave you that wire, to see that it's not magnetic. So we said that a magnet, such as the one you have in front of you, has a north pole and a south pole, right?
Yeah.
And we said around this magnet, and you've seen this before, around this magnet, the magnet causes. What does the magnet cause? It causes a magnetic field, but how do we represent that magnetic field? With field lines, right? And there's two ways we can represent it, either with vectors, so say each little point around the magnet is some kind of vector in some direction. We can say that here the magnetic field is in that direction, here it's in that direction, here it's in that direction, etc. We can see that we're going to get, if we extend these lines, then we can essentially get the field lines we're talking about, right? So we can say they're vectors, and the length of the vector determines the strength of the magnetic field, right? Yeah. Okay, so that's one way to represent it, but we're more interested in representing it like this, yes? So we say it comes out of the north and goes into the south, and we say the magnet has an area where it has some influence. We say that is the magnetic field.
Yeah.
Yes? Now, we say at some point, so closer to the magnet, or closer to the pole specifically, you can see these lines are denser. They're closer together, so we say that those are
More straight.
it's stronger, sure, they're stronger, and we say that what is higher than the magnetic? What's the word that we use? Flux. The flux, right? So what is the flux density is the magnetic field strength, right? B. Yeah. So, okay, that's all good and well. But what do we mean by flux? I mean, when we say flux, what does that really mean? Flux has nothing to do with magnets. It's essentially the amount that goes through a certain area. So if we can represent this very differently. You can say the amount of water that flows through a pipe. If you have a very small amount of water, then you have a small flux, you can say. If you have a large amount of water flowing through the same pipe, then you say you have a higher flux. Okay, so the same with the magnetic field. The more of these lines that fall normal to an area, the higher the flux. Yes? And therefore we define flux if we, let's say we have some kind of area and there's lines coming, let's say there's air molecules here, right? Air molecules, and these molecules fall, how should we sketch them? They fall towards you. So these molecules come towards you, they go through this area. They're coming out of the ball, right, towards you. And we say, well, there's a certain amount of flux. Now, how do we make this flux higher? By having more air molecules coming through the same area. Right, so we can say if we have the same area, this is L by L, this is L by L, we can say let's increase the number of air molecules coming through. And we say then we increase the flux. Right? Now, what would happen if I have to turn this sideways? So now you're looking at the side. So the air molecules are still there, right?
Yeah.
But now I have, let's say, I turn it to the side, so this is what you see, right? You just see the side of that area. But that area does not really exist. It's just an area in space that I've chosen. Okay? There's nothing around it. There's no lines. There's nothing to define boundary. I've just chosen them. So, and these particles move in this direction, but none of them pass through the area of my defined boundary. So I can say the flux is essentially 0. There's no flux in that area that I've chosen. Right? I can do the same thing with Tiffany. I can say I choose an area 1 meter by 1 meter, let's say, right? And I say you stand there and you must throw balls through this area at me. And I catch them. Right? And I get Claire to do this as well. And so I increase the flux of balls through this area. And I get Lewis to do this as well. I'm increasing the flux. But now I'm clever. I turn my area to the side. Right? You're sitting parallel to this area. Can you now throw balls through this area?
Yeah.
No. But Lewis can still do it. Right? Because he's got some little area to work with here. Right? So he's got some kind of angle. And we know that that angle for magnetic field lines is given as the cosine of theta. Right? So we have the field. What is the field? The magnetic field. Let's go back to the magnetic field. It's represented by B, the flux density. Right? So we say we define our flux then as the field times the area. Right? So we chose an area. So we can choose an area by itself. Right? We can say what area we're going to use. Doesn't matter which area we use, larger or smaller, cosine of theta, depending on whether it is normal. So if it's normal to, or if it's 0 degrees to the normal, then we just say this is, so it comes in perpendicular, right? 0 degrees to the normal. And we can say this angle is 0. And what is the cosine of 0? It's just 1. Right? And if we turn it slightly to the side, then we'll get some angle, let's say cosine of 30. And we see what happens to the magnetic flux. It decreases. Because cosine of 30, we know from our cosine graph, right? Goes down. So let's say there's 0 degrees and there's 30 degrees, right? And there's 90. And if we know that we are parallel, then how much area is available for the flux to travel through? Nothing. If this is cosine of 90, that's just 0. Okay, so that's just a little definition that we've spoken about before of flux. Okay, so we use this is flux. That's fair enough. And then we moved on. This is like, so we'll say this is the first part of what we need to know for electromagnetic induction. Faraday's law, right? Which we've spoken about. Now, that's good and well, but we also spoke about forces on a wire. We said that we can define the force, the magnetic force, on a current carrying conductor. When we speak about current, we mean electric current. Yes? Not displacement current or current of another object. We just mean current of electrons. We said the force is given by, you guys can remember this, VIL. Where B is the flux density, and we said flux density is measured in Farad. No, this is not capacitance. Tesla. Right? We said, what is the next one? I. And we know I is our electric current. And we also said L, where L is defined as the length of the wire. Just the length? Yes. Or the length in the?
No.
The length is in the magnetic field. So the length, this is in ampere, right? And we said that's the length in the magnetic field, and that's just measured, as always, in meters. The SI unit, yes? But we know from flux, we know that if the angle of the current, if you like, or the flow of electrons is not perpendicular to the field, then we have to decrease the amount of force that's on it. So in this case, we saw that that is the sine of theta. So if it's not normal to the field, then we saw that it decreases, the force decreases. Okay, so we spoke about this and we said, well, this is true, and you answer exam questions as if you know this, as if you've seen this, as if you believe it, without actually seeing whether it is true. You just believe me, right? Yeah. Just why would I lie to you? But would I lie to you? We can see if I would lie to you. So, okay, so what do we have here? Now, what type of current comes out of the wall? AC current. Now that's a problem if we want to test this relationship, yes? Why? Because Because I is going to change direction, right? And if it changes direction, then we expect the force to also change direction. So we need a DC current. So what to do? How do we change an AC to a DC?
Rectification.
Rectification is the right answer. Well done for remembering that. Okay, rectification. We work with different types of rectification. Do you remember this? Yes, what do you remember?
Bridge.
A rectifier bridge circuit, sure.
And
we have that little rainbow
halfway.
Rectification, and then we can add a capacitor into a parallel with a resistor. And what was that? That's if it's not half-wave rectification, then it is full-wave rectification.
Yeah.
All right. So we have. And what do we call the device that does this? This is something you might not know. It's called a AC to DC converter. Okay. So all it does is it has a circuit in here with a resistance and a capacitor that changes the circuit from an AC to a DC. So AC comes in, but we know that AC flows half in one direction half the time and the other direction the other half. And that causes my capacitor to be charged. Remember that? Yes? Okay, we will get to that as well and a little bit later. So let's first see if my relationship of force on a wire is indeed true. Let's see if that is true. So, okay, now to actually have this effect be clear, we need high current. When I say high, this gives me a current of about 2 amps. Is 2 amps a lot?
Yeah.
Why?
Can hurt me.
Can it hurt you? It can kill you. Okay, so if you ever do this experiment by yourself, right? Don't try this at home, kids. They say it. But if you ever do this, try not to wear rubber gloves or try not to touch the wire. While you're doing this, okay? If you can open the wire like I have. Because anything up to, let's say, anything from 50 millivolts that goes directly to your heart can actually stop your heart. Okay, but your skin has a resistance, so it usually won't kill you. Okay, your skin has a high resistance as well. So most of the current will actually be used by your skin, which is where you feel that shake when you touch a wire. And I'm sure you've done that, right? Do you know what a 9-volt battery is? You've seen these 9-volt batteries, not the normal 1.5 volt batteries. 1.5 volt looks like this, right? So you've got the 9-volt batteries that have these little, the positive and the negative up at the top. You've seen these in the shop?
No.
No? Okay, you guys don't use batteries as often as we do as kids. So this is a 9-volt battery. I think I have a 1.5 here, but not a 9. So this is the normal 1.5. So you've got the positive potential on one side, yeah?
Yeah.
And the negative potential here. On opposite side of the battery. And when I touch this with my skin, nothing happens, right?
Yeah.
It's alright. I'm completing the circuit. But it's such a small current that flows through these batteries, I don't even feel it. But a 9-volt battery, if you touch, if you put your finger at the top, it's just a higher potential, right? When I finger at the top, I don't actually feel anything because my skin has a very high resistance.
Yeah.
Right? The same thing here is my skin has such a high resistance that almost no current flows. So close to 0 that it's practically 0. 9 volts for my skin, that's true as well. But if you take, that's the skin. Now if you take this battery, put your tongue on it, right? Touching the positive and negative potential, you actually get a shock on your tongue. So your tongue does not have that resistance that your skin does. Okay, maybe I should try that next time. You don't go homework, I'll give you a battery.
That's why we can be killed by the battery.
Well, the 9-volt battery is not going to be. Okay, this is just going to give your tongue a bit of a flinch. We did this as kids all the time. It's just fun for us. Okay, but now here we have 2 amps, dangerous, right? Okay, mostly it probably won't kill you, but let's not try. Let's not see whether it does. So, I know it's fixed. I'm going to tell you that this red wire coming out here is attached to the positive terminal of the converter. So my conventional current will flow out of the red to this little black part here, and through the wire, and to your left, in this magnetic field. Okay. Now, these are magnets, I hope you believe me. I'll show you that they are magnets. Let's see if they are indeed. So something that's, maybe I put glue there, right? I don't know. So let's see if these are magnets. Can you pull them apart? No. Okay, let's see. Let's try strong magnet.
Maybe try.
Go ahead. Ah, there we go. That's not fair. Actually, you can do it. Pull it, hold it. There we go. I was going with you just to see. And look, Lydia. There we go. Lydia. Okay, my boys in the back want to try this as well. That's Newton 3, right? Okay, you were a little bit more careful. Okay, so we all believe me this is a magnet. These two are magnets, right? So why do I want two of those? Why do I not only use one? Why do I place two of these in my little lecture circuit here?
Stronger.
Yes, I'm increasing the magnetic field strength, right?
Yeah.
That's good. So on your magnet that you have in front of you, which side is north?
Red.
Okay, which side is south?
Blue.
The blue. Now, normally it doesn't actually matter which is south and north, right? They're just opposite.
Yeah.
We know that south and south will push each other away. You can, if you don't believe me, try that. South and south. So one of these are actually marked. They're actually not marked right, right? They're actually not marked right. That's interesting. One of these might actually be magnetic. One of them might just be a metal. They're very old, so one of them might have lost magnetic properties, but it's still attracted to a magnet. So let's just make sure that that is indeed true. So let's take this one again. And let's see if you take this one. And I take the south, right? We try to put the south. What do we see? You feel that? Yeah. You count each other, right?
Yeah.
Okay, so this magnet is still fine. Okay, the north and the south are going to be together, yeah?
Yeah.
You can play for hours. Okay, so north and north, I'll put the north at the top, by convention, right? Because we always start with north and go to south. So which direction in this case is my magnetic field moving? Draven, in which direction is my magnetic field moving? Yeah? Yeah. My magnetic field is moving from the top to the bottom or the bottom to the top? From south to north. North to south.
Yeah.
So where is the north? The red one, right? The red one. Look on your magnet that I gave you. Which is the north? The red or the blue?
Red.
The red. Red is the north. So the red is there at the top, right? So which in Fleming's left-hand rule, which finger gives me the magnetic field?
Second.
Magnetic field.
4 fingers.
Which no, this one. Which one gives me the magnetic field?
Second.
The second.
The second one.
This one. Which one?
The third one.
This one.
The middle finger.
Yeah.
Middle, yes, the middle
This
finger.
one. No, this one.
No, middle finger is
Oh, right, sorry. I'm using my own rule, right? Okay, so you use this one as the magnetic field. So which one is the current for you? Okay, I swap them around. You can always also use this as I always remember. I use the middle finger as the magnetic field. I use this as the current. And I use this as the force. That'll also work. Okay, but your textbook will give you this is the magnetic field. So okay, so let's use your textbook method to chase downward in this case, right? Downward. And your current is? Right, because this is the positive terminal, the negative terminal. So conventional current is this way, which means the electrons actually go the other way,
Yeah.
Lewis, but the current is this way. So that would mean my force in this case is towards you. So what will happen to the wire, Lydia?
Why is it?
It's going to move. Do you believe me that if I switch the circuit on,
Yeah.
will it move towards you? Believe me. You believe me? Why? Because you have to? Or because it's true? Well, let's see what happens, right?
Okay.
That's the only way we can know. So, okay, let's hope everything's connected. I've got a small voltage, I'm only putting 2 volts on it. But that doesn't matter, this thing actually gives me a steady 2 amp current. So, you watch carefully, guys, it's not easy to see. It does move a bit because your viewpoint is towards the wire, you can't really see it
Okay, that's fine.
that well, but the guys in front will see it very well.
It's not on.
Let's try it again. There we go. Right? You saw that?
Yeah.
Now what will happen? Again. See if this. Yeah, there we go.
Wow.
See that? Moves toward you, right? So the magnet pushes towards you. As the current comes in from your right to your left, up here, down here. So the electrons move in this. The electrons move in this direction.
Yeah.
The current we say conventional current is in this direction. Yes? That direction. Magnetic field is downwards, and we can see, I know this is not perfectly straight, this is my little setup circuit, but we can see that that wire is almost perpendicular to the field, right?
Yeah.
Okay, so now the field would go from the north to the south downward. Right, so these will connect and there will come field lines out everywhere around it, yes? Just like we had there. Okay, so what will happen if I now change the magnetic field around? What do you think will happen? Draven, do you want to come stand here and try?
No.
Joy.
What will happen if I change the magnetic field around? So let's say now I change these magnets around and now I have myself at the top, my north at the bottom.
Wow.
There we go.
Towards you.
Towards you.
Okay, how do we know that? Well, let's take the left-hand rule again. And we see, what do we see? Okay, not the flat hand rule, that'll be the right flat hand rule. What use this? Okay, so the left-hand, Fleming's left-hand rule with fingers. So if we do this, then we see, okay, you want to use this magnetic field going upwards, right? The current is going in which direction? Still the same, I haven't changed anything here.
Yeah.
The current still goes there, so I would expect my force to come towards me.
Yeah.
Alright, so instead of now moving outward, the wire should, if I switch the current on, move inward into the magnet further.
Yeah.
Let's see if that's true.
Yeah.
You see that? Goes this side. Okay, so we've now proven that it's in fact true. The direction is not that important, but we can see that there is a force in a magnetic field on a certain length of wire, if and only if there is a current. Because you tested the magnet on this, nothing happened. You can't pick up this wire. You try it, nothing. So this is not magnetic. So it has nothing to do with magnetic properties. It's only the current that causes this to happen. Right. Are we happy with that? So we see there is a force. I was not lying to you, which is good news. Yeah. Okay. I hope we can keep that. None of my experiments will show that I was in fact not telling you the truth. Okay. So that's fair enough. So we've spoken about this and we know how this works. So we've done examples. So now let's talk about the other side. So what do we call this one?
Motor rule.
The motor rule or the motor effect.
Oh.
Why is this the motor effect?
Motor.
What do we give to the system? Where does the energy come from?
The
Current. Current, right? We gave the current to the system, the energy comes from the current.
Yeah.
And what did we produce from this current?
Force.
Produce the force. Okay, we produce the force from the current. That's all good and well, but getting a current is the difficult part, right? So getting a force is easy. I have hands, I can push this wire with my hand. Why do I care if I have a current, right? I can just push it with my hand. That's not difficult, but who cares about that? Who cares about that? That's not important. What is important, or more important, is that we can produce a current if we give so we produce a force given a current. So if we give a watt, we can produce a current. What is the opposite of giving a current, producing a force? We can produce a current by giving a
Force.
inside